Hello, calculus student. This video is for 4.7 part 1, apply optimization problems. So calculus can be used to find maximum and minimum of a function so that we can tell when is the function reached a maximum and minimum values, so we can maximize profit or minimize cost, or for whatever design we know what measurement would give the best output. So what is the theory behind? How do I know that particular value or the particular measurement is maximum or minimum? So there's two approaches to it. One is using the extreme value theorem. So in extreme value theorem, we say there must have a closed interval of a continuous function must have absolute maximum or minimum. Okay, remember, it's a closed interval. It has to be continuous function. Continuous function is not difficult to get, but in a closed interval, that might be a little harder because sometimes our intervals are open, or maybe just from infinity to negative infinity. So there's two approaches to it. If you do not have a closed interval, so you can actually just include the endpoints as a closed interval, and if your absolute maximum and minimum are not at the endpoint, then the interior point will be the maximum or minimum. So that's one approach. The other approach is to find the local max and min in an open interval, and if it is the only local max and mins, then it has to be the maximum. Kind of like if you have a parabola, there is only one maximum for the whole thing from negative infinity to infinity. So this is relative maximum, but it would just be the absolute maximum mean. So the important thing is there is only one. Okay. And this is the local maximum mean, but it's only one, then it is a maximum mean. That means if it turns and then it never come back in the whole negative infinity to infinity, then it has to be the maximum of the whole infinity to infinity. So these two approach would be what we use to solve maximization problems. So these are all well problems, and I picked a few types of these questions for example. And if you do your worksheets and you are comfortable with doing it, it should be fine. Okay, but let's look at the strategy. So the strategy for all kind of optimization problem is always introduce all variables that are changes, sketch a figure, and then label all variables. So don't worry that you have to have one variable. You can have multiples, and then draw a picture. And then you determine what you need to be maximized. So are you maximize the profit? Or you maximizing area, then you write A equal if it's area. If it's a product, then you say P equal. Use all the variables that you have that to find that particular quantity that you want to maximize. Write a formula for it to be maximized. It involves more than one variable. And then, of course, when we do calculus 1, it is one variable. Calculus, when we do derivative, is derivative of one variable d dx only, right? So we need another equation. Sometimes we need another equation that relay the other independent variable so that we can write the one that you want to maximize to one variable. So after you write it down, you look at other equation that helps you to rewrite your original variable to one variable. And then after you write it out, you would consider what domain is feasible. So what should my value what should the variable that I'm defining can take on. So this would determine if you have a closed interval or open interval. And then number 5 would be look at if your equation is continuous, and then you find the maximum minimum. When I say find the maximum minimum, this would be the relative, right? Relative maximum and minimum by finding the critical point. That means you find f prime and solve it, and also find all the undefined value. So and then you determine the value is a maximum or minimum. Most of the time we just do p double prime or like the second derivative, and then use second derivative test to determine if it's a relative max or min. And then you can discuss if it is just one relative max, so it has to be, or you will use extreme value theorem and build tables to see if your maximum is in the interior point. Okay. Example 1, find two numbers whose sum is 23 and whose product is a maximum. So there's no figure to draw, but we have two numbers. So we say these two numbers are x and y. And then the product is a maximum. So the first step is done. Second step is introduce variable. The second step is what am I maximizing? I'm maximizing product. So I'll say product equal to, product is x times y. I want to maximize it. And then the third is I have two variables. Obviously, I want to make it into one. So what other equation can I use? This is the main equation. Sometimes some book call it the primary equation. The secondary equation are the ones that you can use to, make this into one variable. So the other one is x plus y is 23. But you are not maximizing this one. You're using this so you can make this equation a one variable equation. So maybe I can write y equal to 23 minus x so that my new equation now become p equal to x times 23 minus x. Or it become a one variable equation 23x minus x squared. Okay, so that's very good. And I want to maximize this value p. So let's think about what is possible for this x and y. Did they say that they are positive? No. Did they say that they're integer? No. It just can be any number. So you would say x can belongs to negative infinity to infinity. So the domain of this function for x is any number. So in your worksheets, so sometimes they would say find two numbers that are positive, then it will be from 0 to infinity. Now this is an open interval, so we cannot use the absolute extrema theorem to do. So we would look at relative maximum and minimum. How do I find relative maximum and minimum? I would do, or local, I call it local, p prime equal to 23 minus 2x. Critical number, right? Critical number is when p prime is 0, 0 equal to 23 minus 2x, because the critical number could be a relative max or min. So, and then I solve it. So 23 equal to 2x, x equal to 23 over 2. Okay, so this is one number. And this is a critical number. So usually we do like those, see if it is a maximum minimum. But I can also use second derivative test to see if it is a local max or min. So I'll do p double prime. From here, it's negative 2. It's always negative. So less than 0. So that means p prime of, 23 over p double prime of 20 over 3 is always less than 0. So it is a concave down. So that means you have a 23 over 2 is a local min, local max, local is a local max. And it is the only one. And that means in all of the domain, it is the highest. So that means it is the absolute highest. So that means it's the absolute max also, right? Because I only have one maximum. I know that it is maximum because the second derivative is less than 0. So so this will give me maximum product P. So the two number would be, what two number would it be? So x would be, this is x. So x is answer here. To get the maximum product, x is 23 over 2. Y is also, you just do it, subtract it, also 23 over 2. They didn't say that it has to be different. So the two number will give maximum product. And the product is what? 23 over 2 square. 23 over 2. And then square is 132.25. This is how you do it. Okay. Example 2 is about a garden, advancing kind of question. So this question talks about you have a garden, you use a stone wall. So this is like the wall as one side of the garden and wire fence. So it's rectangular. I think we assume that it's rectangular. For the other three sides, so we have length and width and width. Given 100 feet of wire fence, determine the dimension that would create a garden of maximum area. So what am I maximizing? I'm maximizing area, which is length times width. And what other things can I use? Oh, I have 100 feet of wire fence. That means 2W plus L is 100. So that means I can replace L by 100 minus 2W. Okay, so plug it back in. A is equal to W times 100 minus 2W. Multiply it out is 100W minus 2W, 2W squared. So this is A. What is possible? What is the maximum possible length? Because I have only 100 wire fans, the length of it could be from 0 to 100, right? So now it should be actually open parenthesis. I should not use 0 length because I would not do a rectangle. But when I study this, it doesn't make a difference if I include the endpoints or I have a closed interval. So I can actually just imagine that this is a closed interval that I include 100 and 0 because it would never be a maximum area. The area would be 0. So I would just treat it as an absolute maximum or minimum problem. Now to do a maximum minimum problem, all we need to do is do A prime, right? Then find the critical number and build a table. So A prime would be 100, the derivative, minus 4W. What are the critical number? Critical numbers are when this is equal to 0. 100 minus 4W equal to 0. That means W equal to 100 divided by 4 equal to 25. Okay, so now we need to find the maximum. So because we are considering the closed intervals, so I can just build a table. You can also do the other method where you say, oh, just do an open interval and then check out if this is one absolute max, and if it's the only one, then it works. But I just want to show you another way of doing this. So W is a 0, 100 the endpoint, because when I'm doing absolute max, that's how I do, right? And then 25, and then this is A. So if A have 0, these are all 0, right? 2W, well, actually, I cannot do 100. It would be a negative. So actually, it is 50, right? Because if I have 2, well, yeah, I should just say it's 50. But it would make it 0, right? 0. If it's 50, then 100 minus, yeah. And then if it is 25, that would be what? 25 times 2 times 25, 50. So 1250. This is the absolute max. We are looking at max. And it is interior, so it must be the absolute max for the open interval also. So 25 feet of width would give the maximum area. And then what is the length? Length is 100 minus 2W is 50 feet of length, give the maximum. And what is the maximum area? A is equal to 1250. It is interior, so it would be the maximum for the interval from 0 to 50. Okay. Do we have enough time for the second? Oh, yeah. Okay. So maybe I'll do the third example in